guys, and welcome back to PyTorch tutorial series. In this video we're going to see the implementation of one of the optimizers that we have covered in a previous video known as gradient descent. So in this section we're going to see the implementation of the training pipeline first. So whenever we try to create a model using PyTorch, we have to follow the syntax for the training pipeline used to construct any kind of model. The first thing that we have to do is to implement all of the things manually without using PyTorch, so that you could see how the implementation works just by using a plain Python and NumPy package. And then we're going to replace each of the code which was implemented using NumPy and replace it with the functions and packages that we've seen in PyTorch. So whenever we try to create a model, the first thing that we have to do is to prepare a data. This data might be a NumPy array or any kind of data that we download online, structured or unstructured data. We have to use the dataset and data loader package from PyTorch in order to pre-process the data and convert it into a tensor when using PyTorch. But for now we're not going to cover this part. We're going to use a simple NumPy array instead of a complicated data set. Second thing that we have to do is to pick a model. This model might be linear or logistic regression. Third, we have to pick a loss metric. This can be mean squared error, or if it is a classification, we have to use either binary or categorical cross entropy. In the previous video, our main topic was about optimizers, and we can construct optimizers using PyTorch, and we can pick either gradient descent or atom. But first, we're going to implement them manually without using PyTorch. So each of these can be done by using NumPy, and we have to compute everything by using the formula. Then we can replace each section by using PyTorch so that we could see what is happening under the hood when calling all of these functions. Fifth, we have to create a training loop, and the first thing that we have to do inside the training loop is to compute predictions by using the model. We pass the input into the model, that's called a forward pass. Then we have to compute the loss by using the loss that we have constructed on the third step. Then the loss computation needs the prediction from our model and the labels or the targets. Then we have to compute the gradients, and computing gradients is just calling the backward function from the loss that we have constructed here. And after we compute the gradients, finally we have to update the weights by using the optimizer that we have selected here. Enough about the theoretical aspect, and now let's start to implement each one by one. So the first thing that we have to do is to import Torch and NumPy packages. Here we're using a simple linear model, and it doesn't even have a bias. The only parameter that we have is a weight, and we're going to initialize that weight to 0. This is the simplest kind of initialization that we can do. So for now we're just implementing the basic concept, so we don't have to worry about random initialization here. Second, we have to prepare the data, and that's represented by X, and here we're just using a simple NumPy array, and then we're passing a list of 4 elements. The data type is float32, and the labels are given this. So our model is just a simple mathematical function, and it takes in an input and then multiplies it by 2 so that it gives us the predictions are all going to be twice of the input elements. So here you can see that the target is going to be 2468. So the thing that our model does behind the scenes is when we train the model, it's gonna initialize the weight to 0 first, and then once it starts training, it's gonna update the weight and try to find the appropriate weight, or in this case the slope for this simple linear model. Once it finds the perfect slope, then it tries to fit the line within the data. So we have covered the first part, which is preparing the data. The second one is to pick the model, and here we're not going to use PyTorch, so we're going to define our own simple mathematical function, which is the weight multiplied by the input, and we're going to call it forward. And this is just a simple model only having one node, and what it does is just multiply the weight by the input. The third step is to construct the loss, and here we're just implementing mean squared error by using the formula for MSE. So we have to find the difference between the prediction and the target. Y is our target. Then we have to square it. Remember that squaring is element-wise operation, so when we square, it's going to find the difference between each of the elements first, between the prediction and the target, and then it's going to square all of the elements. Finally, we're going to find the mean. Mean is a reduction operation. We have covered this in our PyTorch video. NumPy also has its own reduction operation mean, so here we're using the mean from NumPy and not PyTorch. So the formula for MSE is 1 over n and wx minus y squared. Wx is the prediction from our model because it's multiplying w by x. So first we have to perform a forward pass in the input, compute the prediction, then try to find the difference between the prediction and the target, which is y. Then finally we square it and then divide it by the number of elements, which in this case is going to be 4. So when we call mean, it's going to compute the mean. And the gradient, in order to compute the gradient for the parameter w, is by using d of the loss, partial derivative of the loss with respect to the weight. This is the only parameter that we have for now. So we're going to find the derivative of this loss function with respect to w, and that's going to be the derivative of wx minus y squared. Since 1 over n is a constant, we can take it out. And the only thing that we need to worry about is the y is a constant when we take the derivative with respect to w. So first we have to this will be 2. Since it's squared, you take the 2 and move it forward. 2 multiplied by the derivative of wx with respect to w is just x, because x will be considered as a constant and w is a variable since we're taking the derivative with respect to w. Then we have 2 times x multiplied by wx minus y according to the chain rule. Just follow the chain rule that I have explained in the previous video to compute this gradient. Once we get this gradient, we can define the function gradient, and here we need to pass x because we need the x for the computation of the gradient. We need the y, and we also need to pass ypred, which is wx. The prediction is always the output from our model, and our model in this case is wx. So here, by using this formula, we're going to multiply 2 by x, which is this part, and we're going to find the difference between ypred and our target y, which is ypred and y. And we're going to multiply these two and try to find the element-wise scalar product between these two vectors. So we multiply 2 by x. X is already has 4 elements. Then once we multiply, this will be a dot product between this vector and this vector, ypred minus y and 2x. Once we find the dot product, then we're going to find the mean, which is going to divide it by the number of elements, which in this case is 4. So this is going to be the computation of our gradient. Once we find our gradient, the next thing that we have to do is the training. So we can execute the codes that we have covered so far. Now let's see if our function is working. So we're going to call the forward function that we have created here and then pass 5 as an argument. And when we pass the number 5 in our forward function, it's going to multiply the weight by the number that we pass, which is 5, and 0 times 5 is 0. So now our model is just garbage. It's giving garbage results because the weight is initialized to 0, so anything that we give to the model, it's going to give us 0. So unless we train the model and change the weight, it's always going to predict 0, so it's not going to be useful. So here we're going to start the training procedure. One thing we need for the gradient descent is the learning rate. We have discussed this in a previous video, and this is basically the alpha parameter that we just described in detail in the previous video, and the number of iterations is the number of epochs, and we're going to initialize it to 10. So we're going to train our model for 10 epochs. So according to the training pipeline, the first thing that we need to do is to perform a forward pass, simple forward pass. Then we're going to use our function forward and pass x as an argument and get the prediction from our model. This is going to be ypred. Once we get our prediction from our forward pass, the second thing that we need to do is to compute the loss. Here, to compute the loss, we need to pass y and ypred to the loss function that we have created. This is the loss function, and we have used the formula for mean squared error, and we pass the target first and the prediction of from our model second to the loss function. Once you compute the loss, then you assign the result to the variable L. Then we need to compute the gradients, and to compute the gradients, what we're doing is, for now, we're using this formula. We computed this mathematically, and by finding the derivative of the loss with respect to the parameter w. Then after getting the formula, we just wrote a simple code to compute the gradient. Here we need to pass in the input, the target, and the prediction from our model as arguments. That's why here we're passing x, y, and ypred to the function, custom defined function gradient, and we get the gradient dw to make it different from our parameter w. Then the final step will be to update the weights by using the gradient descent algorithm. If you remember from the previous video, in order to update the weights by using the gradient descent algorithm, what we have done was we use w minus alpha, which is our learning rate, multiplied by our gradient. So the short form for this formula will be w minus or equal to the learning rate, which we have initialized in this case to 0.01, multiplied by our computed gradient dw. And this is basically the short form representation of this formula. Now we have finished each of the steps in our training pipeline, and the final thing is just to print out the number of epochs, the weight, and the loss. So the reason that we are printing out the weight is to see the difference in which, in order to see the update on the weights and to see the progress for our model, and the loss, we need to visualize the loss because we need to minimize the loss so that it could be close to zero. In that case, the prediction from our model is getting very close to our target variable, and once they become the same, then the loss will be zero. So let's just see the output from our training. As you can see, it was a very simple model, so the execution doesn't take any time. As you can see, the weight is changing from 0 and increasing towards 2. 2 was the slope for the line that's going to fit our data. So the line y equal to 2x is going to be the correct line for in order to fit our data. So here the loss is going to start very big because our weight was 1.2 for the first epoch. Then it starts decreasing, and by the time it gets to 2, then the loss will almost be equal to 0. Then finally, by using the forward function, when we pass 5, the weight variable is already changed to 2. So any number that you pass here is going to be doubled because our model is just a simple model that just multiplies the input by 2. So it learns the association between the input data and the output, and it understands that the relationship between these two is that the output is just doubling each element of the input. So if I give any number after we train the model, it's going to just multiply the number by 2. So this is going to be covered in a future video in detail where we evaluate our model, but for now we're using a test case to test our model. Now you can see 5 multiplied by 2 is going to be 10, but since our weight, we're only outputting 3 digits after the floating point, there might be some numbers following these zeros, so that's why it's giving us 9.99. If it was exactly 2, then it just multiplies 2 by 5. But this gets closer to 10 when we increase the number of epochs. So the first step was to compute everything manually without using PyTorch, but now we're going to use the help of PyTorch in order to simplify some of the tasks. So the first thing is, instead of computing the gradients manually, in order to compute the gradients by using PyTorch, we can use the AutoGrad package. So everything is the same, but the data, the input data, and we have the target. Here, since we're using PyTorch, we're not going to use a scalar. We have to change the weight and the NumPy arrays into a tensor. Remember that in order to train a model using PyTorch, it only works if you use a tensor data structure. That's why we have learned about the tensor data structure, because any kind of data must be transformed into a tensor before it can be used by PyTorch. So we're going to pass the list that we have created initially into the tensor function, and the data type is going to be float32, and 0 is also a scalar, and it's going to be changed into a tensor. Since we are using PyTorch, in order to tell PyTorch that the variable w is a parameter and not just any other variable like the input or target, we have to pass the parameter requires grad and initialize it to true. So this is the first modification that we have to do before we use any functions from PyTorch. Here, the model prediction, we're using the one that we have created before, but in the future we're going to replace this by using a PyTorch function. Even for the loss, we're using the ones that we have defined previously. We're also going to replace this later on. So let's just run this code, and now when we pass 5 into the forward function, we see that the output is 0. Now this 0 is the multiplication of these two tensors. Now we're going to start our training procedure. The learning rate and the number of iterations has been changed from 10 to 100. Here, the forward pass is the same as before, the loss is the same. One thing that we need to change is, previously when we computed the gradient, we used this line of code. We used our own gradient function, but now we're going to use PyTorch. So the first thing that we need to do is import PyTorch. Then we have to call the backward function from our loss. So here the loss is just a numerical computation, the one that we have defined by ourselves, but we can call the backward on this computational graph because PyTorch tracks the computational graph if you have provided the requires grad equal to true parameter. So when you call the backward on the last variable, it's basically going to compute the gradients with respect to the parameter that we have initialized. So when we call the backward function, it automatically computes the loss with respect to dw. Since we only have one function and it is not that complicated, it's just going to compute a single gradient, the one as we did before by using the formula. So this is basically the same thing as this, but now we're using PyTorch. Then finally, after the weights after the gradients are computed, we have to update the weight. So updating the weights is not part of the computation graph. Remember, anything that you add in PyTorch, if you define the requires grad attribute, will be part of the computation graph. But gradient descent should not be part of the computation graph. Our last function should be the loss. So if I don't use this line of code, and if I just put the previous formula for gradient descent automatically here, PyTorch is going to automatically assume that this W is going to be our last function from our computational graph, and we don't need this to be part of our computation graph because we want it to stop after we compute the loss. So in order to do that, one thing you can do is by using the torch.noGrad. When you call this function, what it does is anything that we put inside is automatically not going to be considered to be part of the computation graph. So we put it under the torch.noGrad method. We have previously covered this in a previous video. Now it's going to become handy because we're using it when we are training our model. Then one thing that we need to remember is we need to change the gradients to 0 before the next iteration. PyTorch automatically accumulates the gradients if you don't zero them out. So if it computes the gradients dl by dw for the first iteration, then on the next iteration is going to add the newly computed gradient onto the previously computed gradient. And if you do that, the gradient is going to be accumulated and explode, and we don't need the gradients to be accumulated, so we need to zero them out before we start the next iteration. Here we're using the variable w, which is our parameter. After we have finished updating the parameter, we need to change the gradients. So if you want to access the gradients for a parameter, you can call the .grad attribute. And if you want to zero them out in place, then you can use 0 underscore. So the 0 function, if you don't use an underscore, is not an in place operation. This is going to replace the gradients variable with zeros in place, which means at the same place in memory. But if you don't use the underscore, then you have to assign it to another variable because it's not going to replace it in place, and it makes a copy. So we can do this by using the optimizer package. I have already shown this in the slide that I made about optimizers, but for now we're using the weights .grad to access the gradients computed for the parameter w. Once you get the gradients, then you can call the 0 in place operation to change the gradients to 0 before the next iteration. So just remember, first we need to define the data, then we need to define the parameter. Third, we need to define the model, loss, and how to compute the gradient. Then once we initialize the learning rate inside the training loop, we perform forward pass the loss, then gradient, then update the parameters, then change the gradients to 0 before the next iteration. Now we're gonna print, since our number of epochs is 100, we're gonna take the mode, when the mode of 100 with 10 is equal to 0, then we're gonna print every 10 epochs, because listing all the 100 epochs is going to take a lot of space. Now you can see we're printing out every 10 epoch, and we're seeing the difference in our weight and loss. Here you can see our loss is basically 0 after 100 epochs, and our parameter w is getting extremely close to 2. So as you can see, this is much better than the ones that we have previously defined, because number one, we're using a larger number of iterations, and second one, computing the gradients using PyTorch is much more efficient than computing this using a NumPy defined function, because each of the multiplication operation that we are performing is going to take some time. Now, when we test our model by passing in a new data, which is 5, into our forward function, now you can see it's not even 9.999, but now it's basically 10, because we have trained our model for 10 epochs, more than 100 epochs. Now we have seen how to replace the gradient computation with a little help from PyTorch. Next, we're going to compute the loss, and by using PyTorch, and the loss computation and the parameter updates using PyTorch. So the code is basically the same, but now we need to import the neural network module. And here, make sure that this is the same as before. We're going to create a list and pass it into the tensor function. We also need to do the same thing for the weight and pass the requires grad attribute. Then here we're going to see how to make the prediction with the help of PyTorch, but for now we're going to make it manually. But for the rest of the cases, we're going to use the help of PyTorch to basically compute the gradients, compute the loss, and update the weights. So our model is going to stay the same. We're going to replace it later on with the help of PyTorch. And here we're just printing out so basically what we're doing here is just separating the two lines of code, and here we're just printing out before we train our model. As you can see here, the output from our model is 0 because we haven't trained it. The first thing that we need to do is to replace the custom defined function loss by using the MAC loss function from PyTorch. In order to access the MAC loss from PyTorch, we need the neural network module. That's why we imported torch.nn as nn. If you don't use as nn, you have to call the entire torch.nn in order to access MAC loss. But if you say as nn, then you can just call it by using nn. Then you're going to assign it to the variable loss. So you can see that this is very much more convenient than the previous method where we just manually computed the loss. But under the hood, this function is basically doing the same thing. And the second thing that we need to do is to replace the optimizer by using some help from PyTorch. In order to do that, we need to import another module known as torch.optim. The optim module from PyTorch gives us access to all of the optimizers that we have covered in the previous video, such as stochastic gradient descent, atom optimizer, and a lot more optimizers. So when you create this is just basically creating an instance of the class stochastic gradient descent, and the constructor function for the class SGD requires two arguments. The first thing is you need to pass in the parameters, and the second one is the list, the learning rate. You need to pass the parameters as a list, and you need to pass in the learning rate. because the optimizer is basically used to update the parameters using the computed gradients. So once you have created an instance, then you can assign it to the variable optimizer. The learning rate was initialized to 0.01. Then the rest is basically the same, so we use a forward pass and make a prediction. The second step is to compute the loss by using the newly created loss function. Remember that we're not using the custom defined loss, it's commented out. Now we're calling this variable. And this variable is basically a function, and it requires two things. The first one is the target, and the second one is the prediction from our model. Then we have to compute the gradient by using L dot backward. Since L is the last function from our computation graph, when we call backward, it's going to perform a backward pass and compute all the gradients. Finally, remember that by using this part of the code, we updated the parameters by using the gradients. And in order to access the gradients, the DWs were computed manually before, but in order to access the gradient, once they're computed, you have to use the .grad attribute from the parameter. So we're using w.grad to access the gradient, then we multiply it by the learning rate, and then we update the weight using these two. So when we created the optimizer, the reason that we pass the parameter and the learning rate is because they're useful when we call the optimizer.step function. So the optimizer.step is basically going to replace this part of the code, and under the hood it's basically performing this computation, and you don't need to worry about writing out each detail. The only thing that you need to do is to construct the optimizer, and once you are inside the loop, after you compute the gradient, then call the optimizer object and the step method. Finally, this is basically the same as before, and we need to zero out all the gradients before the next iteration, so we call the grad attribute of the parameter and use 0 underscore to replace the gradients with zeros. This is an in-place operation. Then finally we print out each epoch. So when we print out every 10 epoch, we can see that it gives us basically the same result as before, and here we can see that the final test case is also giving us the same result as before. So now we have basically replaced every component except the prediction from our model. So the last thing that we need to do is to replace the model that we have created by ourselves and replace it with a PyTorch model. Remember that when we created the input features and the targets before, we didn't need to worry about the shape of the input. But now when we create the model, the linear regression model from PyTorch requires the number of inputs and outputs, so we need to change the shape, and the smallest shape, the number of dimensions that it accepts is, so we have 2. So we have to, since the number of dimensions for the previous list was just 1, we need to convert it into a list of lists. So in each number we're going to add square brackets. This means it's going to be a list of lists, and each square bracket represents a sample, and this is going to represent the number of rows. And if you have more data, such as this is going to be each row represents each sample. So the number of rows are going to represent the number of samples, and the number of elements that you add in each bracket is going to basically represent the number of features, because each training sample has, for example, this one has 2 features, but for now, to simplify things, we're using 1. So this is one modification that we have to make, and even the test data that we're passing has to be converted into a tensor, and we have to use a list because it has to be the same shape as the input data. Previously we're just passing the number 5 because it's just we didn't have to worry about the model, the shape of the model, but now we need to modify the test case. Then finally we can check the shape of our input data. So by using the shape attribute of x, we can get the number of samples and the number of features. And in order to see the shape, we can print out x.shape. You can see that the number of samples will be 4, because we have 4 samples, because we have 4 rows, and 1 represents the number of features, the number of elements within each row. And when we print out the number of samples and number of features, we can see that the number of samples is 4 and the number of features is 1. Finally, we can assign the number of features to our input size and the number of features again to our output size. Remember that in our model it accepts 1 input and gives us 1 output, so that's why we're defining the input and output both as the number of features. It's basically dependent on the number of features for your model. So the thing that we didn't replace before was a forward function that we defined by ourselves. This was basically our model. But now we're using the linear regression model from the neural network package to create a linear regression model. Remember, now you don't need to define the parameter by yourself, because the linear regression model from PyTorch has a weight and a bias. Here, previously we didn't use a bias, but now when you define the linear regression model under the hood, it initializes random weight and bias. And we're going to assign this to the variable model. Now, by using this new model, we can pass our test data to see the output. Here you can see that the prediction before we train the model, when we pass 5, which is our test, this is why we converted the number into a tensor, because we're passing it into the model, and the linear regression model expects a tensor and not a single number. And after we get the prediction from our model, we're going to get a tensor. So in order to change the tensor into a number, we can call the dot item method, and this will give us the number itself. Remember that if you don't use the dot item method, it's going to add the tensor function in front of the number. Now it's giving us a garbage output because we were expecting that 5 must be multiplied by 2 to give us 10, but now it's giving us -3 because the randomly initialized weight and bias from the linear model wasn't good enough. So in order to train our model, we have to use the MAC loss from the neural network package, which we replaced in the previous section. Then we initialize the learning rate and the number of iterations. Then we initialize our optimizer. Before, remember that we pass W that we have created by ourselves as an argument to the optimizer that we created. But now the model itself contains all the parameters that were initialized. So in order to get access to those parameters, what you need to do is to call the .parameters method of model. In order to see what they look like, we can print out the model.parameters. You can see that it's a module it's a generator object. But you cannot see the parameters initially because this is just a generator object, and in order to see it you have to convert it into a Python list. And now once you convert the model.parameters into a list, you can see that this generator object was converted into a Python list. The first parameter was our weight, and it was randomly initialized to -0.6721. And the second parameter is our bias, and it was initialized to 0.2110. And you can basically modify these parameters by yourself. And I have already described it in the theoretical videos that I made about optimizers. So that's what we are passing here, and this basically contains the weight and the bias, and we need to pass the learning rate as a second argument to our stochastic gradient descent and construct our optimizer object. Then in our training loop, on the forward pass, instead of using our user-defined function, which was the forward function, now we're using the model, and we're passing the input into our model to get the output, which is ypred. Then we need to compute the loss, which is still the same as before, by using the loss that we have created here. And we need to pass the target and the prediction from our model as attributes. Finally, we need to compute the gradients by calling the backward method from the last variable. And in order to update the weights, we have to call the optimizer.step as before. And finally, one modification that we made here is previously we just used the parameters themselves in order to zero out the gradients. We used the .grad to access the gradients of the parameter and then used the in-place operation. But now, by using the help of PyTorch optimizer, it has a function known as zeroGrad, which basically does the same thing to the gradients. So this is much more efficient than the previous method, so we have to use this one. And that's basically it. We don't have to do anything else. And finally, we just get the model.parameters. Remember that this is a generator object, and we extract the weight and the bias from this generator object so that we can print them out here. And the weight is the first, when we access the first element, it's going to basically be the weight. and we're going to extract the number from the list. So here you can see that it's basically a list of lists, so that's why we're calling 0 and then 0 to access the first element. And then we need to print out the loss so that we could visualize the update to the weight and the loss. Finally, when we print out the result from our model, you can see that it's getting better and better when we reach 100 epoch. But you can see that this model is performing worse than the ones that we have used before. This is because the initialization of the weight variables was not done good enough. So that's why sometimes you need to do some, you need to make some kind of adjustment to the learning rate, use a different type of learning rate, or change the type of loss function, use a better one, or just change the optimizer. Then once you can also initialize the weights from a normal distribution, then you might get better results. So this is just a simple demonstration. That's why the result was not as good as before. But basically by choosing different parameters, you can improve the result from our model. Finally, in order to check the prediction after training, we are going to pass the test data again, which is 5. And now you can see that the prediction was changed from -3 to 9.479. And that's all that we need to cover in this video. So we started out by implementing the training pipeline for PyTorch manually using NumPy and doing it mathematically ourselves. Then we replaced each component by using the help of PyTorch. Learning in this way will help you to understand what is happening, and if anything goes wrong, you are basically equipped enough to solve any kind of problems that you might approach when you are working with PyTorch functions. That's why I am explaining it in this manner, so that you understand what the requirements for these PyTorch functions. A lot of people make mistakes when passing in the input data. They forget to convert it into a tensor, or they forget to change the shape. So these you need to understand what these functions are doing under the hood before jumping directly to implement them using PyTorch. That's all about the training pipeline for PyTorch and optimizers. Starting from the next video, we're going to cover some simple models such as linear regression and logistic regression model using PyTorch. Thank you for watching this video, and if you like the content that I'm creating, then make sure to subscribe and share with others. Audio Jungle.